I welcome you all in today's practical session of broadband communication systems. Today we will see the second practical. The title is Measurement of Losses in an Optical Fiber Communication Link. So in this practical we are going to measure first of all attenuation loss, second bending loss, and another loss which we call as a coupling loss. So let's start with the first that is measurement of attenuation loss. So let's see about the kit first. So this is the optical fiber transceiver kit we have already demonstrated in the first practical of numerical aperture. So the procedure for establishment of the link is already discussed in the earlier video in that numerical aperture measurement experiment. So you can see again that, or we'll share separate video for the establishment of link separately also if required. So earlier initial procedure was like we connect 1 meter fiber between LED 1 and PD 1 and we establish the link. So the link has been already established. Like when I press SW0, the L0 should be on. When I press SW7, you can see here, when I press SW7, L7 should be on. So this confirms that the link is established between the transmitter, which is LED1, and the receiver, which is PD1. So this procedure we have already done it, okay, before demonstrating this video. Okay, now this is the purpose of this practical is to transmit the analog signal and receive the same. So for that purpose we can see here again there is a provision here at point P11 where we can give the analog input. Okay, so with the help of function generator we'll be giving a signal which is 1 volt peak to peak and 10 kilohertz frequency. So we have taken that signal from the function generator, you can see here, and we have given it to this first IO port. Okay, it is input output. We can take the input, we can get the output also from this port. So we have given this input from the function generator at this point. Now you can see that here there is one more provision that is called IO1. So this and these 2 points are internally connected. So whatever I give it here, it is available here. So now the signal which is 1 volt peak to peak 10 kilohertz is available here. Now I am giving this input to this point P11, which is called the analog input, which we have taken from the function generator. So the input is now given to the trainer kit or this optical fiber transceiver kit. Now before one more important point, you can see that there is a switch 8 where we have provision of digital as well as analog. Now we are performing analog link transmission, so we'll keep this switch 8 on analog position. Okay, so when you want to go for digital link, which is practical later on, the switch 8 will be kept on digital link. Now as already discussed, the purpose is to transmit the analog signal and receive this same with the help of detector. So you can see here LED1 is your optical source, which is transmitter, which is operating at 850 nanometer, and we have connected now 1 meter fiber. You can see that this is a fiber. This is a 1 meter fiber we have connected between LED1 and PD1, which is photodetector 1, which is at the receiver part. Now this fiber will act as a channel and it will carry that analog signal which is sent from the function generator, and that signal will be received via optical fiber at this point, which is called detector point. So you can see that once we connect the fiber between LED1 and PD1, now I would like to see the received signal, which is the output of detector. So here there is a provision. You can see that there are 2 points actually, P32 and P31. So we'll be measuring that output at P31 because if the strength of the signal gets reduced, let's say after passing through that optical fiber, so we can change the gain of that particular received signal also by adjusting this gain knob, which is kept here. So this is P31 point. We'd like to measure the output at this point P31. Okay, now let's see here. We have given the input at this particular point, and now you can see that there is there are 3 provisions here for giving the input and taking the output. This is IO2, this is IO3. Now IO2 is here, so same is available here because they are internally connected. IO3 is here, same signal is available here, so as they are internally connected. So I have given the, let's say, input to this port, and I am checking the output at this port, which is available here. So what I have connected, simply output of detector, which is at point P31, I have connected to this IO3 here, and this IO3 is available here also. So with the help of this, I am now checking the output on the CRO. So sorry, DSO here we have. We can see that on channel 1 there is an input which is 1 volt peak to peak and 10 kilohertz, and this is the output of detector which is at point P31 on the OFT trainer kit. This is the received signal that is obtained as the output of detector. So you can see that same signal with almost same voltage and same frequency we have received. So this is the like initial purpose of the optical fiber transmission with the help of analog signal. Now the second, you can see that the output here, which is received signal strength, will just measure its amplitude. So you can see that at channel 2, its peak to peak value is roughly around 1 volt, 980 millivolt. Roughly, it is almost same, 962 millivolt to 1 volt. So whatever was the input sent, 1 volt 10K, it is available at the output also of the detector. So we'll designate this output as V1. Now, coming back to the formula for calculating the attenuation loss. So we have this relationship that is being given in the manual. We have V3 by V1 is equal to e raised to minus alpha L3 minus L1. Now we have already obtained this output. Which is there on channel 2. This is mark this as V1 because we have connected 1 meter fiber. Okay, and corresponding to 1 meter fiber, this is the output of the receiver, which is obtained as the output of detector. Now, in this formula, we have already let's say obtained V1. Now we'd like to calculate V3 practically. So for that purpose, what we can see, this is 1 meter fiber. I will replace that 1 meter fiber with the help of 3 meter fiber. You can see that this is the output now corresponding to an optical fiber which we have connected as a 3 meter optical fiber. So slightly reduction in the signal strength when the fiber length has increased. Okay, so this particular value will be measuring and we'll mark it as V3. So we got V1 by connecting the fiber of 1 meter. We measured that on channel 2. We got V3 now by connecting fiber of 3 meter, and we designate it as V3 now. So using this relationship, we are not concerned about the power. So we'll use only this relationship. V3 by V1 equal to e raised to minus alpha L3 minus L1, where L3 means length of the fiber, which is 3 meter, and L1 means length of the fiber, which was initially 1 meter. So just putting the values V1 and V3 and using this expression, we can compute alpha using calculator easily. Okay, so that's all about the first loss, which is called attenuation loss.